Hello and welcome to lecture 13 of the plasma physics course. Today we're going to pick up from where we left at the end of lecture 12. And in particular, what we were working on was what we call the pressure gradient force. Let me put that in writing for you. And we were evaluating the loss of pressure, or rather loss of momentum, from the particles on the right of our fluid element. We're talking about electrons. I'm going to refer to them either as electrons or particles in general. And we're looking at the electrons that are coming in and out of our fluid element at on the right side of the fluid element. So here is what we're doing: electrons entering and exiting the fluid element at x plus delta x over 2. Could have typed that. Oh, well. And what we got by summing over the various types of particles is that that loss of momentum is given by this integral for all value of wx of me times w times wx times the distribution function of the electrons calculated in R, W, and T, where the integral is in dw. As a reminder, we define three different velocities in the system, or in our description of the plasma, that are in no particular order: the particle velocity with respect to the lab frame, the fluid element velocity, again with respect to the lab frame, and the difference between the two. We called the first one V, the second one U sub E, and the third one is W, where U sub E is the average of V by definition. It's the average velocity with which the particles in our fluid element are moving. And again, by definition, the average value of W is going to be 0. Okay. End of the reminder. We need to calculate this integral. Now, in order to calculate that integral, we need to know the distribution function. If we don't, well, then there is no way to move any further. But we can make a simplifying assumption that is going to give us some results. And that assumption is that the distribution function is a Maxwellian in W. Let's see what that means. I'm going to spell it. It's going to be faster than trying to write the symbol. If I spell it right. Wow. Distribution, okay. Function is a Maxwellian in W. This means, and I'll let you think about it if this is not obvious, that the distribution function is, if we wanted it in terms of v, the particle velocity, then the distribution function is going to be a shifted Maxwellian. In other words, the distribution function is a Maxwellian in the frame of reference that's moving with the average velocity of the particles. And in that frame of reference, the velocity of the particle is W by, again, definition. And therefore, I can make a coordinate transformation and go back to a lab frame and find out what the what my distribution function looks like. And that's still going to be a Maxwellian, but a shifted Maxwellian. Not going to go any further in this. But what we now can observe, looking back at this integral, is that if this function is a Maxwellian, this distribution function is a Maxwellian, it's going to be an even function of W. Therefore, when I have my product, W times Wx, this is going to be equal to Wx squared in the x direction plus Wx, Wy in the y direction plus Wx, Wz in the z direction. And these two integrate to 0. And the reason why they integrate to 0 is that they are odd functions integrated over an even integral. In conclusion, we only have one term left, which is the first one. Now, looking back up here, we're going to have in the x direction a terms. Let me call this integral capital I. So I don't have to write it again. My integral is going to be equal to a term. Remember, this was an integral over space of a vector, so the result is still going to be a vector. That vector is going to be in the x direction. And the integral is going to look like this. It's going to be mass of the electrons times Wx squared times F, which is going to be a Maxwellian, I'm going to indicate that with that subscript M in dW. And this, by definition, is the electron pressure. We did not go through the transition from the statistical distribution, the distribution function type of description of the plasma to the fluid one. But I hope that you know from statistical mechanics that if you take that and take moments of that distribution or the equation for the distribution function, you're going to end up with various terms that have a precise physical meaning, and pressure is one of them. Okay, then, so what we found is that the total loss of momentum from particles on the left, sorry, on the right, other left, and this is per time unit. Let's see if I can make this work. That's going to be equal to what we just calculated times the surface. That is, it's going to be moment lost in the x direction, and the amount that is lost is going to be equal to delta y delta z times the electron pressure calculated. Sorry. At x plus delta x over 2. And this makes sense because I'm finding that the loss of momentum over time, which needs to be a force, is given by a pressure times an area. And therefore, dimensions are correct. Okay. Then we're pretty much at the end of what we need to do. The next step is to repeat the calculation on the opposite side. Now it's really the left side, x minus delta x over 2. But I hope you are going to be easily convinced by the statement that this is going to be identical. The procedure is going to be identical to the calculation that we just did. And therefore, I'm just going to write the result. That's now going to be a gain momentum. From electrons entering and exiting the fluid element on the opposite side. Let me emphasize the difference. This again, and this was, well, this was a loss. Okay. So the difference is going to be the total force on my system, and the gain in momentum on the left side of the system is going to be given by this same expression. It's going to be in the x direction. It's going to be delta y, delta z, because that's the shape of our fluid element. It's the same on both sides, times the pressure, but now the pressure is calculated at x minus delta x over 2. Then my total force which I earlier called the pressure gradient force, but we'll see that we get a gradient in a second, is going to be given by delta y, delta z, I can factor that, times electron pressure at x minus delta x over 2 minus electron pressure at x plus delta x over 2. Now, where did that minus sign come from? Well, we calculated the loss of momentum, but remember the pressure is going to be a positive number. And so is the area, delta y times delta z. That is electron pressure at x plus delta x over 2 times delta y times delta z is a positive quantity. Therefore, when we need to enter it into, when we go and enter it into our equations, we have to remember that we're calculating a loss. We know that that is a loss term, and therefore take the magnitude and put stick a minus sign in front of it. But now this is equal to, I can multiply and divide by delta x. Do it in the next line. So I take a delta x out, multiplies delta y, delta z, gives me delta v. And then I pull a minus out, so I can use PE calculated x plus delta x over 2 minus PE calculated x minus delta x over 2. And all divided by delta x. Then I take the limit for delta x going to 0, essentially. Then my total pressure force plus that. Is going to be equal to minus delta V dP. Oops, that was bad. This is a vector. Partial derivative of the pressure over in dx, and the force is itself in the x direction. And then I realized that there wasn't anything special about the x direction, just the one that was convenient. And for that reason, I can repeat the calculation in the y and z directions, and it's going to be identical. My pressure force is going to be equal to minus delta V times grad P. So that's where it comes from. Last but not least, we got one more to go, and then we can wrap this all up. Is what we called the collisional friction force. So it's the force between ions and electrons. So let me type that. I hope I used this color in lecture 12. I can't remember. Yes, okay, great. I went and looked. Collision and friction force is going to be a little easier to calculate. We can assume that the ions are faster or slower than the electrons. Derivation is the same. It's just to fix ideas. Assume that the electrons are moving faster than the ions. It's just for convenience. And also because it's typically the case. Now, the velocity of the ions is less than the velocity of the electrons. Well, that's a force that's going to come from collisions. And let's see how we can express it. We already talked about collisions. So let's remind ourselves what those collisions did, and let's see what we can write about this force. Now, it turns out that we didn't really do this, but what we get from a single collision between one ion and one electron is that the change in momentum of the electron will depend on the difference in velocity between the electron and the ion. If they're moving with the same velocity, that change in momentum is going to be zero because they're not going to collide. And I pause for a moment to decide how deep to go into this. We don't have time to go deep at all. We'll have to take it as a reasonable result that the drag force is going to have this expression. I promise will be easier. And I was thinking I will just state the result. But then I asked myself, should I actually do any derivation? The answer is no. We'll just take it in faith. That's going to be proportional to the volume. And then mass of the electron, that is the momentum of the electron, and E, that we need for dimensional reasons, times the density, how many electrons are experiencing this. And here is the critical piece. We are going to introduce this average collisional frequency. We did see its expression earlier. I don't think I wrote the whole thing, but let me write it now. If I didn't, I have square root of 2 over 12 pi to the 3/2 times E squared and I divided by epsilon 0 square me to the 1/2 times t to the 3/2 times what we call the Coulomb logarithm. You probably remember this expression or something like this. It's in our textbook too. The reason for using this collisional frequency is actually that we're going to define it precisely so that we can use it this way. We could define averages in different ways, but this is what is going to make the drag force have a simple expression. And notice that this is drag force on the electrons. We said that the velocity of the electrons is larger than the velocity of the ions. Then the minus sign means the electrons are slowing down. That makes sense. We're going to have an equal and opposite force on the ions. That was it. That concludes our derivation, which I optimistically thought we could do in a lot less time, but here it is. The conservation of momentum equations, we can write them both because we did the derivation for the electrons, but we can easily accept that the derivation for the ions is the same as long as we keep track of signs, especially charge signs. And this is what it looks like. ME and E. This one is with the subscript E, obviously, for the electrons. Plus U sub E dot grad U sub E, the inertia piece. This is equal to the Lorentz force, E plus U E cross B minus grad P. First time we calculated today, minus the friction force, ME and E nu EI UE minus UI. And for the ions, we have a similar equation where we just replace the subscript E with the subscript I, and we replace minus E with E, the charge of the ions. Here it is. This is going to be E times N ions times E plus U ions cross B minus grad P ions plus M E M I. No, sorry. Oof. I'm making a mess. M E and E. We define the collision frequency so that the total loss of momentum of the electrons will be proportional to the density of the electrons. The density of the ions appears inside the frequency, as you can still see on top of the page. So I could define a new EI and get the NI out of the of that expression and put an NE inside, but that's going to give me the same result. And same for the mass of the electrons, mass of the ions. I switch them around. Okay. So this term, what is important is that they're equal and opposite. That is our system of equations in all its glory. Of course, this gets combined with the continuity equation. And of course, as you may hopefully know from statistical mechanics, we're going to have the same problem that we always have. We have an equation for correlating the density and the velocities in the continuity equation. Then we have an equation for the velocities that's given by the momentum equation. But that depends on the pressure, which we don't know anything about. So there are various options that we can take out of that problem. All right, then. Here are our two options. we put in a closure, which is not an equation of state. That's going to be particularly important in ICF. Or we write an equation for energy, or if you prefer, for conservation of energy. That's going to give me an equation for the pressure. And I'm not going to derive them, but the equations for conservation of energy are derived in the same way. It's a bit of work. It's quite a bit of work, actually. Oops, I didn't realize that my text disappeared. All right, sorry about that. So our two options are, again, the closure, which is not an equation of state, and an equation for conservation of energy, or one equation per species. And those will look like this. 3/2 of NE times the time derivative plus U sub E dot grad. Okay, this piece is the usual piece, times the temperature of the electrons plus P sub E del dot U sub E, divergence of the velocity, plus del dot Q sub E is equal to S sub E, and similar for the ions. I'm just going to tell you what these symbols represent. The first one I'm going to write is the last one actually in the equation. This is going to be sources and losses. Fusion could be there, radiation could be there. Those are the places where equation comes or into the system or leaves the system in either direction. The term before that is the heat flux. If there is flux of heat into the system, then the energy of the system will increase or decrease. We had a similar point to observe talking about conservation of energy for a single particle. The energy of the particle is not conserved if I'm doing work on the particle. And then the other terms are contain quantities that you already know about. Now, I can use an equation of state to relate temperature, pressure, and density. In other words, the temperature is not a new unknown. I can express it in terms of the pressure. It's just more convenient to write it that way. However, I don't have anything for the heat flux. I can make assumptions on the shape of the heat flux, and that's going to be a different type of closure. But if I don't, I need to carry on my derivation and figure out what's the conservation equation for the heat flux. And as you may know, every time I do this, I'm going to end up with some quantity that I need to define to find out from somewhere else. So at some point, you need to break the chain and say, I'm going to make an assumption for this quantity, and that's going to be it. For the other option, I remind you this was option 2. We we can just say something like this, that P over N E. No, I don't want to write that way. Sorry about that. I need to assign some function f of N, E, and P. In principle, this could actually include something else, but we're not going to get into that level of detail here. That could be, for instance, P over N to the gamma is a constant, or something of that kind. Where gamma is some number that I'm going to give you. Okay, so great. That concludes our hand wavy for this last part, but rigorous elsewhere derivation of the equations for the fluid equations for ions and electrons. Again, the energy equation for the ions looks identical, replacing the subscript E with the subscript I. And now we're going to take one last step. Let's try to make it happen quickly, to go from this set of equations, which is already a lot easier than the full distribution function equations for the field distribution function would have been, to something even simpler, where we do not distinguish between ion and electrons anymore. We just consider the plasma to be some type of single fluid, some whatever mixture, your favorite sauce with whatever the ingredients are, ions, electrons, what else, it's just a single sauce. Okay, challenge is to do this in 20 minutes. Let's see what we can do. I could have cheated and written this ahead of time, but I felt bad about that, about doing it that way. Now we're going to try to reduce our two-fluid equation to a single fluid. This is done in a way that will give us what is called the MHD model, which is actually pretty much the only thing we can get if we want a single fluid model from the model we've written so far. This will give us the MHD, and I spelled it out, magnetohydrodynamics model. A few assumptions I'm going to need, and maybe will not have really the time to get into the detail, but for length, we're going to have some length A that's going to be much larger than the Larmor radius. Now, Larmor radius, which one? The one of the ions that's going to be much bigger itself than the Larmor radius of the electrons. And then we're going to make an assumption on time scales. And I can call this an assumption on frequency, which I'm going to express as follows. The collisional time between ions and electrons is going to be, collisional frequency is going to be much less than the thermal velocity of the ions over A, where A is my scale length for the process I'm looking at, which is going to be itself much less than the omega cyclotron ions, which is itself much less than the omega cyclotron of the electrons. If you prefer, I can call these gyration frequencies. And I'm also going to assume, lastly, that the velocity of the ions is much less than the velocity of the electrons. That means that's automatic if, let me call it thermal velocity of the ions is much less than the thermal velocity of the electrons, which is itself much less than C. I'm not going to worry about the relativistic pieces, and the velocity of the ions is much less than the velocity of the electrons. That's automatic, as I was saying, if the temperatures are of the same order. Now, it may not be terribly obvious, but the step that will work here is formally we can neglect electron inertia, or take the limit for the mass of the electrons going to 0. We make it clear that this is, oops. This is the assumption that will let us write the total ion mass and mass conservation as conservation of the ion masses in practice. Then I can define a mass density rho, which is equal to the mass of the ions times n. And since I only have one fluid, there is no way I can distinguish between the density of the ions and the density of the electrons. That is, n ion is equal to n electrons is equal to n. That's if I have singly charged ions. If I have multiple charges, you just have to take that into account and put a factor of z in there. Then I'm going to define the plasma velocity as the velocity of the ions. That's where the assumption, the neglecting the electron inertia comes in. And for the reason that I've run out of letters, I'm going to call it V again. And this is going to be equal to U sub ion. I suppose I could use it, call it U without the subscript, but anyway. And notice that you can actually calculate the electron velocity by observing that the current density is given by E times N. Remember, we said the N's are equal, U sub I minus U sub E. The current produced by the electrons summed to the current produced by the ions with the proper signs. And wrong one, no, turn the thing off. This, even if I neglect the information about the electron, tells me if somehow I can find the plasma current, then since U sub I is equal to V, I can solve this for the velocity of the electrons. And that's the solution. It's going to be V minus J over E times N. So this is going to give me the velocity of the electrons. Then I'm going to define a total pressure. Okay, this one is very creative. P is going to be equal to PE plus PI. Let me make clear that this is a P monster. P sub I. Okay, then I can go and look at the mass conservation. Sorry, the mass conservation for ions, and that's pretty much the mass conservation for the whole plasma. I just multiply by the ion mass, and I obtain that d rho over dt. Remember the definition of rho. I think I should probably square them so that we can remember that these things are important. Okay. Plus here I had U sub I dot grad that turns into V dot grad, bring the mass in rho, plus rho times divergence of V, and all of this is equal to 0. And often we use this shorthand d dt plus V dot grad is equal to total derivative with respect to time. And that's the reason why you will also find this equation written as follows: d rho over dt plus rho divergence of v equal to 0. That's my mass conservation equation. For momentum now, we add the two equations up here together, and you see that the last terms go away because they're equal and opposite. Great. P and pi sum to just give me P. And if NE is equal to NI, then the electric field disappears from the equation. And the last piece, the other piece in the Lorentz force, gives me a current. And the first term, the term on the left-hand side just gives me the mass conservation for the plasma. I hope that was detailed enough. Maybe I can write it a little bit more in detail. But here is what we find. That momentum conservation reduces to rho dv over dt with the definition of derivative I have up here. This is going to be equal to J cross B minus grad P. Remembering the definition of J, what you do is group the velocity of the ions and velocity of the electrons. They both multiply the magnetic field, and you have an E times N in front. Remember again, Ni is equal to Ne. That just gives you the current. And that is all you have for the momentum equation is this expression here. And this expression gives you force balance in the plasma. So that's going to be, especially when we do MHD equilibrium calculations for a fluid fusion experiment. That's the most important one. I'm not going to get any further. There are actually two more things that we will need to do, but maybe we'll get there once we come to the use of these equations. We'll just do what we need then. Here's what I need to do. Still need to add the Maxwell equations to my system. I'm not going to write them. And a relation between J and D, if you like, an Ohm's law. This could be an ideal Ohm's law. That's okay. But if it's not, then I need that equation too. And that's going to be all that we have time for now. I will point out that what I called a closure earlier, I'm not going to show that. Just keep that in mind as useful information to prove that the two are not completely unrelated and making no sense. What I called a closure earlier, and the specific example I gave you for a closure, can actually be derived from the energy equation if we set to 0 the sources and the heat flux. So the two, again, will give you the same type of information. The 0 heat flux closure in the absence of sources is what will give you that. I didn't name it as such, but what is called the adiabatic closure, where gamma is going to be in the adiabatic gamma of 5/3. Could be a different number, and then you get a different closure. Okay, speaking of closures, this is a good place to stop for us. We did cover a lot today, and we're done with this part of the course. There was sort of an introduction. In a couple of lectures, we went over fluid equations, where they come from, and so on. And now we are ready to move on. Thank you, and I will see you in lecture 14.